Welcome to Pharma Drama, the channel where we look at the science of healthcare and healthcare products. In this video, I want to recap the use of different physical forms in making medicines. By that, I mean the advantages and disadvantages of crystalline and amorphous forms respectively. In this way, you should be well set to answer any type of question on physical form and medicine design when doing a pharmacy exam. So, if that sounds good to you, get yourself a drink. I am in the laboratory as ever, and so I'm not allowed to have a drink, but you can, unless you are also in a laboratory, and let's make a start. Crystalline and amorphous materials are the opposites of each other. So a good place to start answering any question about physical form in medicine design is with some basic definitions. So let's do that first. In a crystalline material, the molecules are arranged in a repeating pattern and are defined by unit cell. In an amorphous material, the molecules are randomly arranged. That means a crystalline material has a crystal lattice energy, that is the amount of energy holding the molecules together, and an amorphous material does not. This means amorphous and crystalline materials behave very differently, and they both have advantages and disadvantages when we put them into medicines. So let's look at both, starting with crystalline materials. In a crystalline material, the molecules are arranged in a repeating pattern, and we define that pattern with a unit cell. If there is more than one way the molecules can arrange themselves, there's more than one unit cell, and we say the material is polymorphic. Different polymorphs have different properties. In particular, when we melt a material, we have to put energy in to break the bonds holding the molecules together in the crystal lattice. Therefore, if we have different polymorphs, they have different crystal lattice energies and different melting points. We can rank the relative stabilities of the polymorphs in order of their melting point. The one with the highest melting point is going to be the most stable. All the other ones are said to be metastable, and the further away the melting point becomes, the less stable that form becomes. Why is this important? It's important because when we dissolve a crystalline material in water, we have to break the molecules apart to get it to dissolve in water. And so the form with the highest melting point has the highest crystal lattice energy. It's the hardest to break apart. So when we measure the solubility of different polymorphs, we find the solubility of the most stable form is the lowest relative to all the metastable forms. If we measure how fast that crystalline form dissolves, we will also find that the most stable form dissolves the slowest. Slower dissolution is going to lead to less bioavailability in a human. So if we were to make a tablet, or multiple tablets with different polymorphs of a drug, we will find the more stable the polymorph, the lower the bioavailability. So, you might say to me, okay Simon, I've got lots of different polymorphs of a particular drug. Wouldn't I just choose to formulate a medicine with the least stable polymorph? Because that one should have the highest bioavailability. And that would be true. That's one advantage of polymorphic materials. We can choose a form which is less stable because it should have higher bioavailability. Do we always do that? The answer is no, we don't always do that. The reason is because the pharmaceutical industry is a risk-averse industry. You're giving things to patients and we don't want to kill them, we want to make them better. In particular, we might give a patient a box of tablets and they might keep that in their shelf for 2-3 years. And when they come to take those tablets, we want to make sure the tablet is going to behave the same as when it was freshly made. If you think about the drug in a tablet, there's really two things that might happen to that drug on storage. One is it will chemically degrade, and really there's not a lot we can do about that. And if it's chemically degraded, it's not there anymore, so it can't have an effect. And two, it might change its physical form. And by change its physical form, I mean if we have a series of polymorphs of different stabilities, then nature tends to prefer the most stable form. Therefore, if we make a tablet and it contains the drug in its most stable crystalline form, it's never going to change. It's got nothing else to crystallize to. So we can be pretty certain that the stable crystalline form is going to be a stable tablet. However, if we make a tablet with a metastable crystalline form, because we want fast dissolution and high bioavailability, if that tablet on storage, the drug changes to a more stable crystalline form, what's going to happen to the bioavailability? It's going to get worse, isn't it? Because it's now a more stable form. And in fact, on storage, it's changed the form that we didn't want in that medicine in the first place because we wanted a better performing tablet. So what that means is we have this dichotomy between faster acting but less stable and more stable but slower acting. So whenever we're making a tablet with a crystalline material, we have to make a decision. Do we want a fast acting product but we take a risk with it on storage, or do we want a slow acting product which will be fine on storage? And that is usually going to come down to how well is that tablet behaving with the most stable crystalline form in it. If, even though it's the slowest dissolving form, that tablet still gets enough drug into the body to exert a pharmacological effect, we're going to go with it, aren't we? Because why would we not? It's not going to change on storage, and it's having a medicinal effect, and that's perfect, isn't it? On the other hand, if it simply doesn't dissolve fast enough in its stable form to give us the therapeutic effect that we want, we have to formulate with a metastable form. But then we have to take the risk that on storage it doesn't convert to the more stable form, because if it does, the product loses its performance. So if I was writing an exam answer about crystalline materials, I would point out that one good thing about crystalline materials is that there can be polymorphs available, and different polymorphs means we have flexibility in choosing which polymorph to use. The less stable the polymorph, the faster the dissolution rate and the higher the bioavailability. But the risk is on storage, it converts to a more stable form and we lose that benefit. That's the sort of thing I would put in an answer about crystalline materials. There are some other things. I mentioned chemical degradation in particular. And although we can't necessarily stop a molecule degrading with time, it's usually the case that the more stable the crystalline form, the more stable it is chemically. So we can also think a little bit about improving chemical stability by choosing crystalline materials. So that's what I'd put for crystalline materials. Let's have a think about amorphous materials. Amorphous forms are more tricky. We can't define the structure of an amorphous form because the molecules are randomly arranged and there's no crystal lattice. But that's the main advantage of an amorphous material. Because they have no crystal lattice to overcome, the main barrier to dissolution isn't there. So if we were to measure the dissolution rate of all the different physical forms of a drug available, we will find the amorphous form is going to be the fastest dissolving. Because of that, fast dissolving means higher bioavailability. So again, if we were trying to make a product act as fast as it can in the body, the amorphous form is the way to go. So the main advantage of an amorphous material is that crystal lattice energy isn't there, there's no barrier to dissolution to overcome, and so we get fastest dissolution and higher bioavailability. Now, if you were following the discussion that we've just had about crystalline materials, you'll remember we had this balance between long shelf life and fast acting product. And what I said is longer shelf life is usually associated with slowest acting product. Slowest acting because it's the most stable form. Can you see therefore what the main risk of formulating in the amorphous form is? How to think? It's going to be stability, isn't it? We're going to make a product which is incredibly unstable, and it's the instability which is leading to its good performance, but the instability is never going to go away. And so the main risk of making a tablet or any other formulation in the amorphous form is that on storage it crystallizes. And I think you might imagine that if it were to crystallize on storage, we're going to lose the performance of the product. So the main risk or disadvantage of an amorphous material is that it's going to have poor stability. There are things we can do to improve the stability. We could add polymers in there, for instance, to stop it crystallizing and things like that. But the main thing to note, I think, in an exam answer about amorphous materials is they're going to be unstable. There are a couple of other things you might note. Typically with an amorphous material, because the molecules are quite randomly distributed, there's quite a lot of space between the molecules, and that means that amorphous materials tend to be quite hygroscopic. That means they absorb a lot of water from their surroundings, and if the drug chemically degrades by hydrolysis, that's not a good thing, is it? You've got a material which is susceptible to degradation by water, and you put it into a physical form where it's going to absorb water, right? Those two things don't go well together. And even if an amorphous material doesn't degrade with water, water is what we call a plasticizer, and a plasticizer is, in simple terms, something which encourages the material to crystallize. So the trouble with an amorphous material is it has a propensity to absorb water, and that water makes it crystallize. And so you're trying to make it stable, you've got to do something to stop it absorbing water. So quite often you'll see a desiccant in a packet of something, and that tells you that the product is particularly sensitive to water. So to sum that up for amorphous materials are relatively unstable, that's a downside, but that instability is what leads them to be fast dissolving and gives them higher bioavailability. So if you can find a way of stabilizing an amorphous material on storage, it's going to be the best acting product. Right, I hope that made sense. Really, all you've got to remember is, when talking about physical form for medicines design, you always have this trade-off between fast acting and long lasting in terms of stability. And the pharmaceutical industry is risk averse. If you can make a product which has acceptable performance and it's going to be very stable on storage, that's the way the pharma industry is going to go. And you're only going to move towards metastable crystalline forms or even the amorphous form if you have to. And the reason that you have to is because you simply don't get a therapeutic effect with your product if you use the most stable crystalline form. So whenever you're thinking about answering an exam question about physical form and medicines design, think about that balance. In particular, you must read the question. You must answer what the question is specifically asking you. So those are the general terms, but read the specific question and see if you can construct an answer along those lines. Right, I hope that helped. If it did, please hit the like button and consider subscribing. It really helps me out and the channel out. Otherwise, good luck in any exams that you're taking, and I'll see you again soon.